then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, Precalculus students, and welcome to lesson number 4. So today we're going to look at domain of functions again. The previous lesson, we looked at domain of functions, finding domain of functions from an analytical perspective. Today we're going to look at finding domain of functions from a graphical perspective. So that's pretty much what we're going to do. Before I get to finding domain from a graphical perspective, I'm going to do a few review problems over finding domain from an analytical standpoint. So let's take a look at some. All right, so I'm gonna go through these fairly quickly. There'll be somewhat of my last example, my last review problem will be fairly interesting, but the first few are gonna be pretty straightforward, so I'm gonna just go through them. So here's some function f of x. So let's say f of x is x to the 7th minus 3x to the 6th plus 14x to the 5th minus 77x squared plus 918, and that's over x minus 5. So there's a function, and we want to find the domain of f of x. So again, for right now, there's two things that give us restrictions on our domain, and those are our denominator being 0, any value of x which makes our denominator 0, or there being a negative number inside an even radical. So numbers inside an even radical must be greater than or equal to 0. Those are the only two things we're concerned with right now to cause restrictions on our domain. There are other things that can cause restrictions on domain, but for right now, those are only two things we're concerned with. So in this case, I don't have an even radical, but I do have a denominator with a variable in it. So I just need to make sure that that guy is not equal to 0, which means x cannot be equal to 5, which in interval notation would be negative infinity to 5 union 5 to infinity. And that should seem fairly straightforward based on what we did yesterday. And also, I'll do two examples at once. So let's say f of x is the 6th root of 10 minus x. And let's say also h of x is the square root of 2x minus 12. All right, so those are two functions. We'll find a domain of each. So for this first function, I'm going to work it out. But again, as you get more familiar with these problems, generally a lot of these domain problems, you can just look at the problem and tell the answer. Like I can just look at this and tell that's going to be negative infinity to 5 to infinity. It's not a whole bunch to think about. And same here, I can look at this and tell it's going to be negative infinity to 10, and I can look at this and tell this is going to be 6 to infinity. And so that's kind of where we want to get you, where you can kind of just look and tell. But I will work it out. So this guy, this is an even radical, so I know the stuff on the inside must be greater than or equal to 0. And then I'm just going to solve. So negative x is greater than or equal to negative 10. I'll divide by negative 1. X is less than or equal to 10. And less than or equal to 10 is negative infinity to 10, like so. Now, one thing you can understand, you know that these even radical problems deal with greater than or equal to 0. However, if the x has a negative number in front of it or a negative sign in front of it, that means you're going to have to divide or multiply by a negative number to make it positive. And so that's going to change the direction of the inequality symbol. So for all these even radical problems, when the coefficient of x is negative, it's always going to end up being a less than problem, always. And it's fairly easy to see that that number is going to be less than, it's going to be 10. Now, if the coefficient of x is positive, then it's always going to be a greater than problem. And I think it's fairly easy to see that that number is going to be greater than it's going to be 6. But I mean, I can work it out if you want. So this would be 2x minus 12 is greater than or equal to 0. So 2x is greater than or equal to 12. So x is greater than or equal to 6. And in interval notation, that is 6 to infinity. Okay. So these are things that should have been pretty routine for us. I want to do one more review problem. This one's a little bit different, so I want to see how you're going to handle it. And so for my last review of finding domains analytically, I want to use this function f of x. So f of x will be x minus 4 over x squared plus 16. So x minus 4 over x squared plus 16. So you haven't really seen a problem exactly like this, even though the same principles arise. So that's the good thing about mathematics. No matter how you change the problem, the same principles hold. So I want to see what you think about the answer to this problem. So, and you may have to think a little bit. So I want you to pause the video and figure this one out. When you come back, I'm of course going to work out the answer. Okay, so just thinking about the type of different answers that I tend to get on a problem like this. So some people may say negative infinity. That's not a good negative infinity. And these are all wrong answers, by the way. Some people may say negative infinity to 4 union 4 to infinity. My infinities look a little jacked up, but you understand my pain. Some people may say negative infinity to negative 4 union negative 4 to infinity. Some people, and I'm pretty impressed that some people did this, even though it's wrong, but it's a very beautiful looking incorrect response. Some people may say negative infinity to negative 4 union negative 4 to 4 union 4 to infinity. Very beautiful, but yet incorrect. So these are all wrong. And so if your answer was one of these, you were wrong. And so what is the answer, you may say? Well, the domain of this function is negative infinity to infinity. It has no restrictions. It doesn't have an even radical, and there's no value of x, which would make your denominator 0. Look at it. This is x squared plus a constant. We're talking about real numbers that we're plugging in. Every real number squared is positive. So a positive number plus 16 will never be 0. So there's no value of x you can plug in, no real value of x you can plug in that will make your denominator 0. So it'll never be 0. And if you were, actually working it out, you would say x squared plus 16 cannot be 0, which means x squared cannot be negative 16. And from there, you can't solve that with real numbers. You can't take the square root of negative 16 with real numbers. You can with complex numbers, but when we speak of domain, we're speaking of real numbers, so you can't. So this will never be 0, and so therefore our domain is negative infinity to infinity. All right, so each of the next few days, we're going to bring a little different nuance to finding domain with these, finding domains analytically. So let's get to the deal for today, which is pretty simple, unfortunately, and that's going to be finding domain from a graph. So let's look at some of these graphs we want to look at. All right, so here's what we have. This presentation is a modified presentation of me doing domain and range. So it says domain and range, but we're only going to look at domain today. We're going to look at finding range from a graphical standpoint in the next lesson. So for today's lesson, albeit that says domain and range, we're just going to be looking at domain. So I took all the range slides out. Okay, and so when we look at domain, so a domain are if you think about how we did it analytically, it was the x values that we plugged into the function, what x values it could take. Well, the x values corresponds to the x-axis from a graphical standpoint, which is a horizontal axis. And so therefore the domain would represent the left and right endpoint of that particular axis. That tells you the extent of which you can go. Now, of course, within those endpoints, of course, you can have points where the function could not equal a certain number, which you can have open circles of such things within an interval. That is possible. I'm not going to show that today, but that's definitely possible. But the main thing we're kind of going to look at today are the left and the right endpoints of where the function starts to where the function ends. All right. And I'm not doing range today, but it's going to say here what the range is, which of course we're looking at the y-axis. And for the range, we're looking at going from the bottom to the top versus left and the right, because range deals with y, and y is a vertical axis which goes up and down versus going left and right like the x-axis, which is horizontal. All right, but we're not going to actually do any range today, but that's kind of what we look at for doing range. So now we're going to pull a few graphs up and going to analyze their domain. And again, remember that brackets mean the number is included. Parentheses mean the number is not included. When looking at a graph, a closed circle represents a number that's included. An open circle represents a number which is not included. And if you don't see an open circle, I mean, you just see a smooth curve, that of course means the number is included. So the only way to show that the number is not included is to use an open circle. All right, let's look at our first graph. So there's our first graph. So we're just going to simply find the domain of this particular graph. And again, domain, I'm looking at the x values. What x values can it take? And I look at the left endpoint. So you look over here to the left. And again, you want to look at the values on the x-axis when looking at domain. You see the left endpoint is -7. And then you go all the way to the right, and you see the right endpoint is at 8. So this domain is just all real numbers between -7 and 8, including -7 and including 8 because of these closed circles. And how do you write that in interval notation, you may ask? It's just -7, 8. So that's how this is written. So when there's an interval between two finite numbers, it's just a smaller number, comma, the bigger number. That's how we write it. And again, if the numbers have a closed circle on them, they'll have brackets, an open circle, they'll have parentheses. Let's look at the next problem. So again, we want to look at the left endpoint to the right endpoint. Again, when we're doing domain, what we don't want to do, I'm emphasizing this because this mistake happens all the time. What we don't want to do is look at the y-axis. We're looking at the values on the x-axis. So the left endpoint, hopefully you see, is -3. So here's the left endpoint right here at -3. And the right endpoint is right here at +3. You should also notice these are open circles. So the numbers are going to have parentheses. So parentheses -3 to 3. That's the domain of that particular function. So you're probably catching on to this, and these other ones we can probably go through a little quicker. It should be quite obvious as we look. This is not the most difficult thing in the world to do. So for the remaining examples, see if you can find the answer before I say the answer. Pause the video when you need to. So for this particular problem, -7 to 6, parenthesis on -7, bracket on 6. So that's how that domain looks. Next example, -7 to 8, bracket on -7, parentheses on 8. That's how that guy looks. Let's look at our next guy. So this one, you don't have any stopping point. You don't have open or closed circles. Open and closed circles signify a stopping point. Here we have arrows. So that means that this particular graph does not have a left endpoint because it doesn't end. Nor does it have a right endpoint because it doesn't end going to the right. So what do you think its domain would be?
negative infinity to infinity. Our next graph. So on this graph, what do you think is the left endpoint? What do you think is the right endpoint? And hopefully you thought negative infinity to infinity. Next graph. So this one is a little different from the previous two because we do have a stopping point on the left, but we have an arrow on the right. So again, interval notation goes from least to greatest, from left to right. So we should start at -3 with a bracket on -3. And where do you think we're going to end? Infinity, because of the arrow. So -3 to infinity. And our final graph, this is a fairly quick and easy lesson. So there's our graph. Again, one has a point and one has an arrow, but in this case, it's not stopping going to the left. So it's going all the way to negative infinity. So this domain should be negative infinity to 4 with a bracket on the 4. So I hope this was understandable. This is our 4th lesson. This concludes our first week of learning. So what you should have come to realize is once we cover something, that material appears on all subsequent assignments. So we covered something on Tuesday. It was on Tuesday's assignment, and that stuff was also on Wednesday's assignment with the new stuff from Wednesday. And then Thursday's assignment included the stuff from Wednesday and the stuff from Tuesday. And today's assignment includes the stuff from the previous days, and that will continue on into the subsequent weeks. And so I do this to make sure that we truly master material, so we keep seeing it over and over again versus seeing it one day and then asked to be tested on that material 2 or 3 weeks later. We're seeing the material every day over and over again. It helps to increase our understanding. But we thank you for your time. We thank you for the hard work you have displayed thus far. We know this remote learning could be somewhat of a challenge, but it looks like some of you are truly learning and truly working hard, and we'll see you next time.